Okay, in this chapter, we're going to discuss the momentum of objects. And generally speaking, when we apply a force to an object that, for example, has no friction or friction can be neglected, then the object will acquire momentum. Um, Generally, also, we can say that it is when the net force is not equal to zero that we have momentum. So, for example, if I apply 10 newtons of force to a ball on the billiards table, then that object will respond with the increase in its velocity. And we're going to talk about different aspects of that in this chapter. Um, we're going to talk about impulse, which is the product of the force acting on an object times the time duration for which that force is applied. We're going to discuss how that results in changes in the impulse, in the momentum of a particle. And we'll talk about the effect of what happens when the object bounces off of another object and imparts momentum through that mechanism. Uh, Finally, we're going to talk about collisions, and regarding collisions, we're going to discuss the rule or law of conservation of momentum, first discovered by, or first described, or most eloquently described by Isaac Newton. And these collisions that occur between two objects, which generally we can think of as, not generally, but specifically, the simple example is one of a cue ball on the table hitting a billiard ball. And when that occurs, we can describe the collision as being elastic. And if there is heat involved or during the collision, then it becomes more complicated, and we will discuss the resultant inelastic collisions as well. Now, quite generally, we can regard momentum as the property of moving things. And without loss of generality, we can say quite simply that it is the mass times the velocity. That gives it a vector quantity. Momentum will have a vector, a direction, and a magnitude, which depends on the direction and magnitude of the velocity. Remember that mass is a scalar quantity, so it only multiplies it by a number, or it only multiplies the velocity by a number to get the momentum. And this is what the concept we will use in the following slides. So in this example, we see that a boulder rolling down an inclined plane will acquire momentum as it goes down, and it will continue to increase its speed or velocity as it goes down the hill. And because momentum is the product of mass times velocity, the momentum of a large boulder will be larger than the momentum of a small boulder rolling down the hill. You remember that objects that are either rolling down a hill or falling free fall under gravity all increase their velocity at the same rate. So the velocity of a large boulder is going to be the same as the velocity of a small boulder when starting from rest. And at any given time after it has started rolling, the velocity of the small boulder will be the same as the velocity of the large boulder. As a result of this, because the velocities of the two objects, the small and the large, are the same, the large boulder will have more momentum. And that momentum is a property of the moving particle. And then finally, of course, that any object that is at rest has no momentum because it has no speed or velocity. Now, in this slide, you're asked to answer the question of whether a moving object has momentum, energy, speed, or all of the above. Now, we have not discussed energy yet, but the energy we're referring to here is called kinetic energy, which means that it is the energy of motion of a particle. And just as momentum is mass times velocity, Energy also, or kinetic energy, also depends on the on the speed of the particle. So, jumping to an equation in chapter 7, we can say that the energy is equal to 1/2 the mass times the velocity squared, or the square of the speed. And because all of these depend on speed, the correct answer is all of the above. Now, I will let you answer this question. I'll put a pause in here so that you can think about it, and we'll resume on the slide labeled impulse. Now, as this slide shows, we can define a new quantity, which we call the impulse. It is equal to the product of the force applied to an object times the time duration for which that force is applied. So in equation form, we would just write it as F times T, and it will have units of Newton seconds, or Newton's time seconds. As we will see shortly, this will cause a change in the momentum of a particle when this force is applied. It is important to realize, however, that the implied idea here is that we can neglect things like frictional forces, that when we really use the equation impulse, force times time accurately, we mean the net force acting on an object, or the net force times the time duration. So in this simple case, for example, if you push an object with the same force for twice the time, then we will impart twice the impulse and produce twice the change in momentum. However, it's important to also realize that we are assuming here that the frictional force is zero applied to the object, and so in this case, the net force is exactly the same as the applied force. So it's important to realize that in most of this chapter, we will not include or discuss the effects of friction. Although if we did, then it would simply be the applied force minus the frictional force. And in that case, we would still get an impulse if the net force is greater than zero. Now, as you can see from this slide, as if we apply a greater force to an object, that will generate a higher impulse applied to it, and that will have a resulting change in momentum of the object which is being applied. Now, in this case, it's important to realize that when we talk about the change in momentum of the car, we have to include not only the applied force, but the frictional force. So if the gentleman is applying, for example, 400 newtons of force, but the car has a frictional force that is retarding the motion by 200 newtons, then the net force on the vehicle will only be 200. And in some cases, the frictional force could be as large as the applied force, and of course, in that case, the car will not move at all. But generally speaking, if we take the simplest case where the car has no friction at all, then the application of 400 newtons to an object will indeed accelerate or change its velocity and therefore increase its momentum as a result of applying that force over a certain length of time. Now, some practical examples of impulse changing momentum. The case is given by a golfer swinging his club and hitting the ball on the tee. The idea, in order to generate the greatest velocity of the ball, is to extend the swing of the club as long as possible, so that force is continuously applied to the base of the club until the ball is well on its way beyond the extent of the club. So by applying that force for as long as possible, one increases the impulse and therefore gives the ball its maximum velocity. The same is true of a pitcher on the diamond of a baseball field, that when to get the greatest velocity, he wants to um, make sure that the arm is pushing against the ball for as long as possible before it is released from his arm. Obviously, then pitchers with longer arms have a slight advantage because they can maintain contact with the ball for a longer period of time. At the same time, or I should say, by another example, the baseball will eventually, of course, arrive over the plate where the hitter is prepared to hopefully knock it out of the park, and he will follow through with the swing of his bat for as long as possible to change the momentum of the ball from moving towards the catcher to moving away into the outfield or beyond. By maintaining that contact with the ball for as long as possible, he is able to change the momentum more, and thus giving it a higher velocity when it leaves the bat. So in this case, you're asked to respond to the question of a cannonball shot from a cannon, and what will be the net effect of a long barrel compared to a shorter barrel. Well, in order to answer this question, we need to think about what's happening to the ball after the explosion of gas that drives the ball out through the nozzle of the cannon, and or the barrel. And as long as the ball is inside the barrel, the forward force velocity of the gas molecules will continue to uh, apply a force against the cannonball. And so, if I have a long barrel, the force of applied to the cannonball will be greater, and therefore it will emerge with a larger impulse or a larger change of momentum. And from that, you should be able to answer the question. Now, in this question, you're asked to comment on the properties of a fast-moving car when it hits either a haystack or B, a cement wall. And as we know from some common experiences with hitting moving objects hitting a cement wall, the results are quite devastating if we don't have a cushion. And so the haystack does provide a cushion to slow the vehicle, but we're looking now at the specific properties of the vehicle as it hits these two barriers, one being a haystack and the other a cement wall. What we know from this experience is that they both in both scenarios, the car initially has the same velocity when it strikes the object, whether it's haystack or wall. We also know that as the end result, that the car will come to rest if and it will reach a velocity equal to zero. The car may be, of course, extremely crumpled, and there will be a deformation, but the mass of the car has not changed as a result. Only its velocity has changed. So we can say that if the momentum of the car is the same before it hits the barrier, and regardless of whether it's a haystack, which causes the car to slow down more slowly than hitting the cement wall, its final velocity is going to be zero. So it started with the same momentum in both cases. It ended with the same momentum. So the change in momentum is in fact the same for both of those scenarios. Now, because of that, one can conclude that the impulse, or from the equation, or the equation, or the equal concepts, I should say, between impulse and change in momentum, that the impulse applied to the car is equal to the change in momentum. So, in fact, the impulse will be the same in both cases. That is to say that the impulse applied by the haystack will be the same as the impulse applied by the cement wall. However, realizing that impulse is the product of force times time, we know very clearly that when hitting a haystack, the time for which the car comes to rest or stop is going to be far longer than the time for which the car comes to rest when hitting the cement wall. So we know that the length of time with the haystack is much larger, and since both scenarios require the same impulse, we can conclude that the force is been significantly reduced by in the haystack, because the force times time is the same for the two scenarios. And so, no, they do not experience the same force. And in fact, the force with the haystack is much lower, thus allowing the driver to experience less damage. And of course, the car also experiences less damage, since it will depend most strongly on the force of the impact. So by reducing the force of impact, we delay the time for which the car is stopped, and both the car and the driver are safer as a result of it.